Going to Starbucks for coffee while you are at the airport is one of those chaotic moments in life. The line is always gigantic, and you must decide between being on time on your gate or have that delicious cup of coffee. Lucky are the ones who get it there first, right? This scenario is a great example of another popular data structure called queue. In this video, I will discuss the most important aspects of queues, which implementation strategies are available, and what criteria you must consider for picking one wisely. Hi, my name is Ricardo Ferreira, and I'm a developer advocate here with AWS. Welcome back to this series about data structures. In this episode, I will talk about queues. Queues are one of the simplest data structures to understand, as we don't run in short supply of real-world analogies. It is always easy to dive into a data structure when you can create a mental model that mimics something concrete in real life. In fact, this is by itself one of the best advice I could provide to you. Whenever you have a chance and you are studying data structures, try to create a mental picture of at least one real-life analogy. It will help you solidify your understanding. Given the simplicity of queues, interviewers won't spend much of their time trying to get as much as possible from you. Instead, they will probably probe you about implementation strategies and trade-offs, as well as scenarios where you need to traverse the queue to find something. Let's take a look at queues in more details. A queue is a linear data structure that stores items sequentially, based on the principle of first in, first out, or FIFO. This means that data sitting at the end of the list is going to be picked first, and then remove it from the list. The FIFO nature of queues ensures that items are processed in the order they were added to the queue, which can be useful for maintaining fairness or ensuring the correct execution of sequential operations. In terms of internal structure, a queue typically has two ends, a rear or insertion end and a front or deletion end. New items are added to the rear end, and the oldest item is removed from the front end. The structure also maintains a count of the number of items in the queue, which is typically referred to as the size of the queue. Queues are usually implemented using arrays or linked lists. If the queue has a fixed size, it is a better idea to use arrays. But if you don't know upfront the size of the queue, then using a linked list is a better option, as adding and removing elements will require almost no data movement, only link updates. Now let's discuss the queue characteristics. With fixed size queues, or the ones implemented with linked lists, insertion and deletion of any element take all of one time complexity. They provide a great solution for scenarios where ordering is important to ensure the correctness of any program execution. Most programming languages provide libraries that support different variations of queues, including the priority queue. However, due to the nature of queue, you shouldn't use any sorting algorithms to rearrange the elements within the list. If sorting elements is a requirement to be implemented, then thinking about queues is a sign of going in the wrong direction when it comes to provide a solution to a problem. The insertion and deletion of items in a queue are done in the rear end, which makes it inefficient as you would need to traverse the entire list to reach the rear end. To overcome this limitation, you can use a circular linked list as the storage for the elements. However, it will introduce memory wastage with the extra amount of links to be maintained. Queues are not very complicated to understand, but you must understand its purpose and learn how to keep track of the data. Let's see how to do this from the implementation perspective. We're going to start the implementation of our queue using an array as the backend store. So to start things off, I'm going to ask CodeWhisperer to implement a queue data structure using an array. I think that should be enough. I'm going to hit enter and ask CodeWhisperer to start generating the code. Sometimes CodeWhisperer is going to try to complement your comments to provide more context about what you do. You can either accept them or you can simply skip them and hit enter. So that's your way to say to CodeWhisperer, hey, I appreciate your suggestion, but I'm interested in the code generation for this point on. So a queue, which is an array, it sounds correct. And then we need another, that's interesting. So yeah, it's already suggesting which is a common implementation of a queue using arrays, which is keep track of the front, the rear, and the size of the queue. So far so good. I'm gonna hit enter one more time, and then it's suggesting us to also create a member of a capacity, probably to keep track of the size of the queue. Actually, we already have an element that keeps track of the size. So I'm going to remove this because size and capacity can be used interchangeably in this concept. And then given the capacity, I am going to initialize the queue with a new array of that capacity. So far so good. I like what CodeWhisperer is suggesting so far. So now that we have the queue created, let's start implementing the famous operation called enqueue, which is supposed to resemble the operation of enter the queue, and that's why he's famously known by enqueue. So that's something interesting for you to know. I'm gonna close this if, hit enter, and then okay, start adding the data, and then keep tracking of the rear. Okay, so now we have the dequeue operation, which is delete from queue. And then let's see what the implementation so far suggests. Okay, so far so good. So now we have the queue and queue operation properly implemented. Most likely we're gonna need some operations to expose the front here and the capacity, but let's see what CodeWhisperer is still suggesting. So that is important. So usually when you implement a queue, you are going to implement this operation called pick, which is a way for the user to, as the name implies, to pick what is going to be the next element to be added. So this is important because what is the difference from the dequeue? Because the dequeue operation, as you can see here, not only is going to return that data, but also is going to remove the pointer of what is the front and the rear of the queue, right? So because remember, the queue has to follow the fivefold design. So when you actually get the element for the queue, it's going to actually restructure the internal data. So the next time you call the queue is going to pick up the next one. So a pick is a way for you to actually retrieve that element, but without necessarily to return and restructure the internal implementation. So I'm just want to return which element is in the front. So we have the pick, and then print a queue. Yeah, probably is a good idea because we're going to need to print a queue to test things out. And then let's see what else we have. Yeah, the size of the queue. It's important for us to keep track as well. Is check if it's empty. Okay, I'm going to accept it, but it's not that important for our purposes here. And then checking if it's full. Okay, so I'm going to stop receiving this suggestion for CodeWhisperer at this point. I think we have plenty to work with at this point, right? So just to recap, we have implemented the initialization of the queue, and then the operations to add elements to the queue and remove elements to the queue, or should I say, process elements to the queue, which is the operation of not only retrieve the element which is in the front, but also to update the internal data. So the next time you call dequeue is going to point to the next one. So let's see if this is actually working. So I'm going to create here a main method operation so we can test things out. Yep. Okay, I'm going to insert another element here, queue. In queue, I'm going to insert the third element, and then I am going to print the queue so we can, test things out. All right, so far so good. And then we can test later the dequeue operation. So I'm gonna run the code for the first time, and then what is supposed to happen is this. So it's supposed to print all the elements in the order they were added. So that means that if I call, for example, if I'm going to pick, yep, that's it. The result of the operation pick at this point should return the number 1. Why? Because it was the first one that entered the queue. So let me execute the code one more time to see if this is true. Yep, so print all the elements, and then if I'm going to process one, it's going to be the number 1 because that was the first one. So let's see if the dequeue operation is doing what it's supposed to do. Yeah, so Code Whisperer is already whispering what I should be doing, and then I am going to actually call it twice, right? And then I am going to pick, after dequeuing 2 elements, I'm going to pick what's going to be the next one, which should be basically the 3rd element, which is number 3. But anyway, let's see if this is true. I'm going to run one more time, and then let's recap the code. It print 1, 2, 3. The pick, since no one has processed it yet, is going to be the first one, so sound good. The dequeue operation is going to pick up what is on the front of the queue, so number 1. The second call to dequeue is going to pick up what is now the one that is on the front, because remember, dequeue not only return with the elements in the front, but also remove from the list. Remove in a sense that since we are using a fixed array here, is not going to necessarily going to kind of remove the element from memory, but is going to update those internal members here that keep track of what is the front and the rear, right? So that's what I mean by remove from the queue. And this is only relevant if you are using an array as the backend storage. But again, if I call pick, there will be only 1 item left on the queue. So that's why it returned number 3. So that proves that our implementation of the queue using a fixed array is working as expected. Now that we have our queue properly implemented using a fixed array, we're going to do something bold here, which is get rid of the entire implementation so far and then replace it with the implementation of a queue using a linked list. Now, why you would do such a thing? A fixed array is usually a good idea when you are implementing a queue if, as the name implies, you know upfront what is going to be the size of the queue, right? So if you know the size of the queue, you can do what we have done here, right? Well, technically it was Code Whisperer that did this, but we've worked it together, right? So a fixed size, you can actually create here the internal data structure, and then you are going to basically provide a capacity that's going to be the length of the array, right? So if you know upfront, use the array. But if during the coding interview, the interviewer throw at you that, right, in this scenario, we don't know upfront what's going to be the size of the queue, and more importantly, adding and removing elements is going to occur very frequently. So that's probably a hint for you to, okay, in this situation, using a linked list is a better option. So what we're going to do now is to get rid of the current implementation and using the linked list. However, before we move forward, we actually have to go back to our linked list implementation and provide 2 operations that's going to be suitable to sustain this new implementation. Because in the previous episode where we covered linked list, if you haven't watched it yet, go back to the playlist of this series, and then I encourage you to take a look on the episode about linked list, right? We've created, in the end of the episode, what is considered a circular linked list. A circular linked list is a linked list that keeps track of the head and the tail. So why this is important for a queue? Because what is a queue, right? You have to remove from the front of the queue. So what is the front of the queue if the backend stored of the queue is a linked list? Is the head, right? And then new elements has to be added to the rear end of the queue. So what is the rear end in a queue when you implement using a linked list is going to be the tail. So we have the underlying infrastructure for us to work with already here, right? The only thing missing here is that we don't know, we don't have yet an element from this linked list implementation that is going to perform the removing the first element, right? Actually, I don't think we have any actually elements to remove elements from the list, only to add new elements. So what we're going to do now is on the existing implementation of the linked list, I'm going to put it right here, right before the main method. We're going to ask CodeWhisperer to create a method to remove the first element of the list and call this method remove first, because it's more suggestive. And I know that I will remember when I passed over to the queue implementation. All right. Okay, the signature, it's okay. So now we can continue, get the one in the head, and then keep track of the size. Seems to be very simple. So that's one of the beauties of the linked list. Like, it's basically a process of rearranging links, right? So in this algorithm here, if it's checking if the head is new, so if it's new, it means there's no element, so just return. And then retrieve the head and get to the next one, right? If the head is new, then simply set the tail to new and decrease the size, right? So that is going to effectively retrieve the next element, and then we're going to simply return the head. The only thing that I didn't like from this implementation is that we're not actually returning the elements. So this is going to be useful for us to access the data. So I am going to remove this implementation whatsoever, and then simply change the method signature to return an integer, because we need to return after removing. So let's see how CodeWhisperer help us with that. So now it's more suggestive. So it's not only is retrieving the data, it's doing what it's doing before, and then also updating the size, but also returning the data. So this is going to be important for us, because a queue needs to do exactly this in the dequeue operation, right? It needs to dequeue, delete from the queue, return the element, but also deleting from the internal data structure, which in this case is going to be the linked list. And also for us to fulfill the implementation of this operation here on the data structure called pick, right? We need a way to retrieve the first element on the head, but not necessarily deleting it, right? So I'm going to actually ask CodeWhisperer to implement a method to retrieve the first element of the list. That's it. I just want to return get first. Yeah, I like it, the signature. Oh, sorry. Okay, I'm gonna hit enter again because I didn't accept. Okay. And then what it's doing here is essentially going to the head and then returning the current data, right? So I think that's more than enough for us to store the new implementation of the queue, now using the linked list as the backend store. So then I'm going to go back to our queue implementation, and then we're going to effectively replace the current implementation of everything that you have seen here, right? That's going to be very unfortunate, but it's for a good cause, because I want you to have an idea about how this is going. So instead of actually, the only thing I'm going to actually remove is going to be the main method that we have implemented so far. We're not going to use it, but everything else I'm going to simply comment out and then keep the current implementation for references so you can see the reference. So I'm going to comment out this and then remove all the current implementation. No, actually comment out, because that is the equivalent of when we used the fixed array to this. So the pick, printing the queue also, and then checking the size, and then check if it's empty, right? Most likely we're going to have to create some other additional methods on our linked list to fulfill some of those, but we can always go back later to this to see if we're going to need it. So let's go back to the to this, and then we're going to replace here implement a queue data structure using the linked list. And I'm going to explicitly refer that implementation of the linked list we have here by name. And let me tell why this is important, right? Because first of all, the Java programming language has the collections framework, which includes a linked list. And the name is literally linked list, right? So if you don't specify the package here, right, for our implementation, CodeWhisperer is going to assume that, oh, okay, you're going to link a list from java.util, right? And in this case, I want CodeWhisperer to use that specific implementation. So you have to be really explicit when you ask CodeWhisperer to do things. Now that we have updated our main instructions, so let's go back to our, okay, put, so CodeWhisperer is not doing what it's supposed to do, so I'm going to give a hint to CodeWhisperer. So private linked list, which is this one, right? And then this is going to be my queue. So now CodeWhisperer is starting to, oh, okay, now I see what you're trying to do. And then we don't need any more constructor that sets the capacity. Actually, this is not required anymore. So I'm going to comment out this entire constructor. And then I am going to simply start. No, I don't need a capacity CodeWhisperer. Okay, so I'm going to simply start using the currently implementation of the linked list to do my operations. So queue.add. So in queue is basically adding the list. So let's just recap what add does. It's supposed to add at the rear end. So in this case, it's going to the tail and set the next word and node set the previous one. Yeah, so this is using the tail of the linked list to add remove. So it conforms to the specifications of a queue, right? Similar to the dequeue, we're going to leverage the implementation of the remove first we had done, which is where it is. Yep, remove first, we're going to call this, right? So the dequeue operation is essentially going to return queue.remove first. So that's one of the things that is interesting for you to know about CodeWhisperer. If you provide the complete reference implementation to the context, all the suggestions moving forward is going to consider not only the code that you have currently open, but as well what you have provided here on an open tab. So CodeWhisperer knows what to do based on this, right? It analyzes like code method signatures, function calls, everything becomes part of the prompt that's going to be sent to the backend. That's the implementation of generative AI application, right? So the dequeue operation is going to remove the first, and the pick is going to leverage with operation get first that we've created, right? So we're going to return queue get first. Yeah, that's what I needed. And then printing the queue has essentially have to delegate this to the implementation of the printing we currently have on the linked list. Do we have one? We should have, right? Print reverse and then print. So let's do this. Let's do some delegation here. So print is going to call queue.print, which is the print method of the linked list. The size, we're going to delegate to return the size of the linked list. Same old, same old. So return queue.size. Yep. And then check if it's empty. We do have something about that does this on our linked list. If not, we can work with the size operation to implement this. So we don't have it. That's totally fine. So checking if it's empty, we simply can queue that's empty. No, we don't have this method. Queue.size equal to 0. So that this is going to create a Boolean condition that's basically is going to check if the queue size is 0. So yeah, that's empty to me. All right. So we forgot closing the statement here. All right. We do have everything properly implemented right now. So what I'm going to do is an exercise similar to what we have done before when we were testing the queue implementation using the fixed array. But now we've changed the current implementation to replace with the linked list, and then let's start using the list. So we're going to create the queue. Yep, new queue. Probably is doing something similar we have done before. So somewhere it's still live in the memory of the conversation here of CodeWhisperer because it's remembered the operations that we've done before to test things out. The only thing I'm going to do is I don't need like 5 elements. So printing the queue, printing again, doing some picking. Yeah, I think that's more than enough. This is essentially what we have done in the previous test, right? So we create a queue, we've enqueued 3 items, we printed, and then we're going to dequeue 2 elements, which basically is going to pick up 1 and 2, and then we're going to print again. It should print only 3, and then if we pick, it has to be 3, and then print the queue. We don't need to print the queue one more time, so that's more than enough. Let's see if this is working, right? So let's run the code one more time, and then, wow, we have the famous new pointer exception here in our implementation. So that's totally fine. We can debug what is going on. So it's happening because it's saying the queue is new. So basically on the line 26, and then the queue operation is failing to do this. Let's see why. And because we forgot to initialize the queue. So this queue here is new at this point. So we can fix this very easily by creating a constructor, right? So we can create a constructor for the queue, which is essentially going to initialize the queue, right? So that's how we know that we're no longer going to operate here with a new reference. So that should fix the problem. Let's run the main method one more time and see how this goes. Good. Probably our printing strategy is not very intuitive, but we can work with this. So let's recap. We enqueue 1, 2, 3. The result of this printing queue is this, which is 1, 2, 3. And then we've dequeued it 1, 2 times. So that means we've removed the first and second element of the list. So the next time we print a queue, which is the result of this operation print queue, it only shows 3. And then if we print the entire queue again, but not actually, if we print returning a simple pick of the queue, is going to return 3 again. So the code is working, which is good for us. We've successfully changing the implementation of our queue from a fixed array and replace it with a circular linked list, which is the same linked list we have implemented in the previous episode. Now let's take a look in another possible question that you might have in a coding interview session. So the question would be, how would you find the element within the queue that has the maximum value, right? Now, before we jump into the implementation details, let me explain what is the actual nature of this question, right? So you keep that in mind. What the interviewer wants to know is if you fully understand the backend storage of your queue, right? So that means that if you have implemented this using a fixed array, there's a way, an optimized way for you to actually find the maximum element from the queue, right? Which is transversing the array. Or if you have used it, which is the current implementation we have right now, a linked list, right? So the algorithm that you are going to use is going to be slightly different, right? Because the backend storage is pretty much going to dictate the approach you should take, right? So let's start checking here with our current implementation, which is the circular linked list. It is our backend storage for our queue. So let's see how we could solve this problem. We're going to include a new method on our implementation. So I'm going to use CodeWhisperer one more time, create a method to transverse the queue. No, to find the max element in the list, right? So let's see which algorithm CodeWhisperer is going to suggest first here. So the signature is quite suggestive. So the first, there's 5 implementation suggestions here. Let's take a look at each one of them. First of all is trying to delegate the find max to the underlying implementation, which is the linked list, which I am very fan of this approach, because since we are delegating to the internal data structure, we can, in the software engineering world, we can delegate this responsibility to the actual underlying linked list. I think it makes more sense because in there you have much control of what to do. We can do it here, but we could also do it there. So, but let's see which other implementation you also have. In here, you were essentially using, this is probably not going to work. So here, that's a great example. So we suggest an implementation that assumes that you have used a fixed array, which is not our case. So either it's going to be this one, which is we're going to bring all the data from the underlying linked list here, and then we're going to operate on, or we can simply do this delegation process here. I'm going to use that approach because that's a personal preference. You can leave here in the comments. What do you think? In situations like this, you bring the responsibility of the implementation to the current class, or if you are delegating, in the end of the day, to another data structure, you delegate that responsibility for the other data structure. This is an interesting question because sometimes it's not that simple to answer because you might have working with multiple teams, and delegating to this is another way for it to say, okay, I'm going to ask somebody else to implement this behavior for me, and then we're going to simply use it. So this is the part where in the software engineering world, you have to have the team mentality, not only the lone wolf software developer mentality. But anyway, I think this approach makes sense. So since we don't have a find max operation in our linked list, I'm going to go back to the linked list, and then let's see what CodeWhisperer does if I simply, without saying nothing, put a enter here after get first. Right. So get last. So now we have to explicitly ask CodeWhisperer to do what we needed, which is implement a method to, let's reuse the same prompt that we have used there. Right, I'm gonna copy and paste here. All right, find max. Okay, good. I'm going to retrieve the current implementation. All right. Okay. Okay, so it's a simple transverse exercise where it's essentially is retrieving the head as the current element, and then is retrieving the current element, and it's assuming that the first one is the max one, right? And then as it transverses the list, it keeps, and it checks that the other elements somehow are higher than what it was assumed as the maximum one, is going to replace what is the assumption of who is the max, right? And then it's going to update who is next. Once it's transversed the entire list, only one element would actually be considered the maximum one. So that's the one that's going to be returned. So sounds good to me. So that we can go back to our queue implementation now, no more compiler errors, and then we can simply add, let's do the famous, let's create a separation here for us to see the difference. But then we're going to actually put here, after enqueuing the elements, and then we're going to simply max element is going to be queue find max. Yes, that's what I want, CodeWhisperer. Thank you. I think this is good for now. Let's test if, well, now here is simple. Since we're not working with random numbers, we can visually see that, all right, it has to pick number 3, right? So, but let's see if this is true or not, because we need to measure the correctness of the algorithm. Okay, yep. So it's doing what it's supposed to do. So after enqueuing 1, 2, and 3, and then there's a separation, right? And then the max element is going to be number 3, right? So that is the proof that the operation is doing what it's supposed to do. Now, remember, the implementation of this algorithm is not necessarily the biggest problem in the interviewing question. The interviewer wants to know if you have full control of your current implementation of the backend data structure, because sometimes they want to measure, all right, they want to know if you did that implementation intentionally or just because it was the first one that gives in your head. Because maybe in the original question that they may have thrown to you, they might have said, all right, and then after we implement the queue, consider that in the future, we need to actually find the maximal element. So that is the hint that you should use that, all right, while designing and while you're choosing the best implementation strategy, you have to keep in mind that, all right, since I have to find the maximal elements, which implementation strategy is going to be more useful, the fixed array or the linked list? And then you have to kind of trade off this, right? Sometimes it's simple to trade off. Maybe you can kind of use some clarifying questions with them. Like, for example, tell me about it. Is adding and removing elements going to happen frequently? And then they might say, no, we know pretty much how much elements we're going to insert on the queue. So that's going to give you a hint of, okay, in that case, I'm going to prefer using a fixed array. And then fixed arrays and arrays in general provides more efficient algorithms to find the maximal element, right? When compared to the linked list that you have fewer control, and you always need to end up like kind of a transversing the entire list to find elements. So that is something that you have to keep in mind. All right, let's wrap up what you have seen in this episode. A queue is a linear data structure that stores items sequentially, based on the principle of first in, first out, or FIFO, which helps ensure that items are processed in the order they were added to the queue. A queue typically has two ends, a rear or insertion end and a front or deletion end. Queues are usually implemented either using arrays or linked lists. If the queue has a fixed size, it is a better idea to use arrays as the backend data store. But if you don't know upfront the size of the queue, then using a linked list is a better option, though you have to keep in mind the extra amount of memory required by linked lists. Both options offer O of 1 time complexity for insertion and deletion of elements. My suggestion for you is to keep practicing different problems with queues and use Amazon Code Whisperer to assist you with the code generation. Then spend some time studying the generated code and whenever applicable, criticize and correct the code. In the next episode of this series, we will take a look at the stack data structure. If you start watching this series from the playlist, the next video about stacks should start pretty soon. If not, don't worry. I put the link to the next video in the description below. See you in a bit.